How's it going, everybody? Today we're going to cover derivatives and rates of change. The first thing I want to talk about is this whole concept of a tangent line to a curve, and that we use the concept of a tangent line to a curve when finding the velocity of an object, both involving the same type of limit. So there's something special about this type of limit. We call this type of limit a derivative. And we'll see that it can be interpreted as a rate of change in a number of different problems involving science and engineering. So first off, we want to take a look at tangents. And, we know this definition is basically just a definition of slope, the rise over the one run, the change in y over the change in x. So if we have two functions, f of x and f of a, the change in y is really just f of x minus f of a, and the change of x is x minus a, where a represents that value within the function f of a, that would be x, okay? So now if we take a look at a chart here, right, if we take a look at point P, and we'll call point P a comma f of a, right, x comma y, or x comma f of x comma y would be q. And basically at the end of the day here, what we want to do is we want to find the tangent line at a comma f of a. In order to do that, we can calculate the limit as x approaches a, right? So as we get closer and closer to a, as we move closer to closer in a here, x is going to become a. So essentially that's calculate limit. And we'll see that's what's happening here, as this line, or as this point, x comma f of x approaches a comma f of a, or as x approaches a, point Q becomes point P, essentially, okay? And from that, we get this definition here. So the tangent line to the curve, y equals f of x at the point P of a comma f of a. So a comma f of a represents the point that is moving towards, is the point that x is moving towards, right? Then we use this. M, the slope of the tangent line, happens to be the limit as x approaches a of f of x minus f of a all over x minus a. So this is a formula that would be important right now, is when you take a screenshot, you put this in your notes. Okay, so calculating the limit here, given this equation, we have y equals x squared. This is a parabola. We want to know what is the tangent line at the point 1 comma 1. Very straightforward. A represents 1, f of x represents x squared. We're plugging in our values here. So x squared goes here, 1 going here for f of 1, okay? And then x minus 1 in the denominator. And when we do that, we can simplify this. We know that this is really the difference of two squares, and so when we spread it out like this, we can divide the x minus 1 out, and all we get is x minus 1. And then once we plug in 1 for x, since x is in fact 1, we would get 2. So the slope here the slope of the tangent line at x equals 1 in the parabola y equals x squared would in fact be 2. Okay. One piece that I want you to understand here is if you had a graphing calculator and you kept zooming in on this, so this would be the parabola y equals x squared, but if you kept zooming in on that point, notice our windows becoming more and more refined, smaller and smaller. What this actually looks like is it represents that tangent line. So the closer we zoom in on 1 comma 1, this is a little further out, zooming in a little bit more, zooming in a little bit more. What we're seeing is we're actually seeing something that represents the tangent line, and the slope of that tangent line would in fact be 2. Okay. So as we start to talk about tangents, okay, this is just another formula that's going to become more important for us to use, especially with respect to velocity. And it means exactly the same thing that we just talked about, but f of a plus x minus f of a divided by h. The previous slide here, was it this slide? I'm sorry. There's a previous slide here that explains where that formula comes from, but basically when you're plugging things in, you're going to end up getting this formula here. And so as we start, and again, this is something you want to copy and paste and use, but this will play tremendously into any of the velocity problems that we're going to work on here. And basically, f of a plus h minus f of a divided by h. F of a plus h minus f of a represents your displacement, and h represents your time, which is the average velocity here. So these velocity type problems we're going to begin to use, this formula for, okay? So this is your introduction to 6.5. There's a little bit more on 6.5, which we'll cover in class on Tuesday, but it's going to move to our discussion on derivatives and how we're going to use this formula to help calculate the derivative here. But basically, we have our definitions. We're using our definitions. We use the this symbol here. We call it f prime a, is basically the derivative of a, and this would give us the derivative. So the way that we would write this is that at x equals a plus h, then we have h, which equals x minus a, and h approaches 0 if and only if x approaches a. Therefore, an equivalent way of stating the definition of the derivative, as we saw in finding tangent lines, is this. Okay. So we'll talk to you guys in a little bit.